Hey, my name's Aldo. I'll be presenting on RLC circuits and the differential equations that model their behavior. This topic is physics, differential equations, and electrical engineering. The equations themselves, they're second order differential equations. So an RLC circuit is a circuit that has a resistor, a capacitor, and most of the time an inductor. That's what the L stands for. Uh, The resistor opposes current flow and helps control the discharge rate, while the capacitor stores energy in an electric field and charges or discharges exponentially. And the key function of an RLC circuit is that it controls how voltage changes over time. It's essential in many real-world systems, like filtering signals, like in Wi-Fi or audio equalizers, or timing circuits in electrical signals, things like in stoplights or in other type of electrical. Uh, so understanding how these components interact is essential if you're going into engineering and specifically electrical engineering. So looking back on the history of this, it started in 17 or between 1791 and 1867 when Faraday discovered electromagnetic induction. This is the physical basis for the inductors itself. George Simon Ohm gave us Ohm's law, which gave us the resistors, and Gustav Kirchhoff developed the circuit laws that helped us write the equations based on the conservation of energy in the circuit loop. And we can't forget about Pierre Simon Laplace. He contributed work that later became the Laplace transform. It's a great tool for solving differential equations in circuits. And often forgotten is Oliver Heaviside, and he helped popularize operational calculus, which led to the more modern algebraic solution methods. Here's a circuit setup I did actually at San Jose State. Is a school I currently attend. You can see the different graphs of the resistor, inductor, and capacitor. Unfortunately, I couldn't get a picture of the actual resistor, inductor, and capacitor itself. This is just the oscilloscope that shows it. It's a great tool for students or researchers for understanding the electrical signals. But we see that the resistor, or at least we know the resistor opposes its charge flow. The inductor resists changes in the current because of its magnetic field, and the capacitor stores energy and releases it as the voltage changes. And when these are all connected, the circuit's behavior is not linear. Instead, it's like it follows second order differential equations, which you can see is like a sine wave. Now, when deriving the differential equations, we start off with Kirchhoff's voltage law. You can see here's LQ double prime plus RQ prime plus 1 over CQ equals 0. And we divide it by L to get the standard second order ordinary differential equation. As we see under it, right under it, Q double prime plus R over L, Q prime plus 1 over LCQ equals 0. The values for L, R, and C determine the type of roots we get. And these determine the behavior of the circuit. You can see right here in the diagram, the RLC circuit, it's set up in series. So right one after the other. And right on the side, we also see Kirchhoff's laws. So one of the first roots we could have is overdamping. In an over-dampened RLC circuit, the resistance is large compared to L and C. So R squared is greater than 4L over C. Uh, the charge decays towards zero without oscillating, and the circuit returns to equilibrium slowly and pretty smoothly, as you can see. The solution has a form, as you can see right here, QT, C1E, R1T plus C2E, R2T. And overdamping ensures stability without oscillation, but can lead to slow response times in practical circuits. So it's nice for a demonstration or if you want something to move smoothly, but in practice, it's pretty slow. But compared to that, there's underdamping, and this is when the resistance isn't strong enough to prevent oscillations. This gives us complex conjugate roots, as you can see here. And the graph on the side shows how it decays over time. You see the waves start off bigger, and they slowly get smaller over time. We associate this with resonant circuits, tuning circuits, and other naturally oscillating systems. And then we got critical dampening. This is a boundary case where R squared equals 4L over C. So see here that the resistance is equal to the others. Um, it has the fastest return to equilibrium without oscillation. And it's ideal when you want a system to stabilize quickly without overshooting, like in camera stabilizers, mechanical suspension systems, or other some specific signal processing applications. Yeah, and in conclusion, a series RLC circuit demonstrate how a real physical system can be modeled using second order differential equation. The type of dampening, overdamping, underdamping, and critically dampening depend on the resistance, inductance, and capacitance. It's a great example for differential equation students to fully understand the practical aspects of the mathematics and how it could be applied to their careers in the future, especially if they're considering electrical engineering. And yeah.